Right, so it's a conference on cosmological simulations. So let's talk about how to make them useful. First of all, of course, I want to acknowledge the work of many people that have contributed to the various parts that I mentioned. Several of them are in the audience, and in fact, some of them will be talking in more detail on some of the elements that I will be showing. Advertising, so Matt, Shivam, Lucas, perhaps others. Lucia is here. Yeah, well, you recognize all these people. And so let me just say what the goal is, and then I'll talk about how I think we can get there. We're cosmologists, many of us, and one of the amazing things about cosmology is that we have a lot of theory support compared to some other scientific fields. We understand certain aspects of the theory really well. Others are complicated, but we have ways to model, and those get better and better. So computational cosmology, in a nutshell, is we start with some initial conditions, and then use computational models, perturbative or computational models, to predict observations. Oh, and there is a light cone in here. Sorry, Lucia. And it's hidden behind the other stuff. Parts of these models are really solid. Parts of them are models at an effective level, subgrid models, not necessarily microscopic. But they're pretty detailed, and the goal is to simply be able to turn around this arrow. Now, this is not new. People have been trying to do cosmological inference, or have been doing cosmological inference for decades. But the regime has really changed, and I'm going to argue that we're really in a different regime now, and we can do things in a way that is, really significantly different from how we've been doing this for the last decades. Because the way this has been done in the past is to rely on restrictive, analytical, perturbative, or maybe semi-numerical approximations, whereas our ability to simulate the universe has just has increased by leaps and bounds. So, I'm not an observer, and so to me, this image there looks like an observation. But in fact, it's extracted from a computational simulation. So it's just supposed to illustrate the level of sophistication inherent in computational models. But we're not actually using these models at the moment to do inference. So it's very asymmetric. And, as physicists, we like symmetry, so let's make this symmetric. As part of the Simons collaboration on learning the universe, the goal of this really is to work, one way to say that is to work towards a more symmetric analysis with similar modeling for the data analysis as for the simulation. And so as part of that, we have experts in this Simons collaboration covering a wide range of different fields, including astrophysics on a very large range of scales, and methodology like machine learning, statistics. And the opportunity is to use recent ML breakthroughs, which I refer to as a class as implicit inference methods. So methods where we don't necessarily write down likelihood approximations for certain summaries, but we are able to model statistically the data themselves, even all the way down to the map level. And the goal is to prove the principle of doing this kind of symmetrical analysis on current data sets and be ready for the next generation. Okay, so the opportunity that we are trying to exploit here is that we can now fit models to data at a level of detail that would have very recently been unthinkable. And it was very striking yesterday. Everybody's talking about simulation-based inference in talks as if it's been if it had been around for, it's just normal now. But in fact, it's something that's really just happened over the last few years. And the fact that we can, yes, again, yesterday, people were very comfortable with the idea that we have automated ways of finding summary statistics, very informative summary statistics, maybe even close to optimal. Or that we can build posteriors, likelihoods, or extract priors or generate priors for what otherwise would be completely intractable models through various techniques. And in addition, something that hasn't really been exploited yet, but which also is very new, is the ability to do model comparison. Evidence computation for Bayesians has always been a challenging subject, but it turns out when you look at it from this perspective, it actually becomes even easier than doing parameter inference. It turns out basically it just boils down to training some classifiers. And so there are a bunch of references down there that for some key papers that put us into this regime. Okay, so the goal is to build physical generative models all the way to data. And aside from parameter constraints, I think another benefit of this is that it gives us just many more ways to check models. And I think it will ultimately lead to better and more trustworthy modeling because we can actually model all the way to the data. And in fact, this, so I'm very glad to hear this from other people now. Tom yesterday advocated for this in the discussion. This is a slide that I didn't make for this meeting. In fact, I'm reusing this from a talk I gave several months ago. So sometimes people ask me, are we going to get much tighter constraints doing this? Are we actually going to be extracting much more information? I think the jury is still out on that a little bit. I think we have good evidence to suggest that that is the case. We will be getting more information. So likely, yes. Will we get better constraints? Yes. In the sense that we have much more powerful ways to propagate uncertainty, combine multiple data sets, break degeneracies, and capturing the full covariance. I'm saying covariance because everybody knows what that means, but this is not just tied to Gaussian kinds of likelihoods. So about the kind of dependence between different data sets. And we now actually have a few examples of something like this already working and having been applied to data. So I was very pleased to see that the kids team, for example, redid their entire analysis, changing the entire pipeline to use implicit inference techniques and reissued their results doing that earlier this year. Amongst us, there are multiple people that were involved in or are still involved in SIMBIG, which was a precursor to this kind of work on galaxy surveys, focusing on a subset of a particular data set, the CMAS South Galactic Cap, and demonstrating that one can get competitive constraints doing this kind of work. So we have these techniques. They have been, the first applications to data have happened. Let's make it available to everyone. And so Matt, who's going to be speaking just after this, has been leading an effort involving several of the people, almost all of the people that were on that first slide, to make infrastructure available that democratizes access to this. And the most powerful techniques. So here's a quick slide. I'm not going to go through all the details, but it just is intended to make the process much less painful, easier, and build in some best practices, like, for example, checking models automatically, being able to compare different ways of summarizing your data, different backends for doing simulation-based inference, and everything within easily accessible interfaces. So if this seems exciting to you, but you haven't actually had a chance to write your own pipeline, this makes it very easy. You can put together an end-to-end analysis in just 5 lines of Python. And again, if you have questions about that, I direct you to Matt. There are multiple examples for how to use this in this paper, including some examples outside of cosmology, gravitational waves, for example. All right, so have we solved everything? what's the problem? What's left to do? There are two main problems, and first of all, and what I'm actually going to focus on most in this talk is scaling, and the other is model quality. So, because we want to do this. So here's, because this is something we've been focusing on, Rosa made this very nice image of the CMAS data. This is the CMAS sample, largest currently publicly available spectroscopic data set. That's why we're using it. And so you have the North Galactic Cap and the South Galactic Cap. South Galactic Cap is the smaller one there. And just for comparison, I'm showing you here a 1 gigaparsec cube in there. So as you can see, neither the North Galactic Cap nor the South Galactic Cap actually fit inside a 1 gigaparsec cube, but all of our simulations are 1 gigaparsec cubes or smaller. You heard yesterday, some other simulations we use, Quixote, which is the one that everybody uses. Paco's here, we made available in 2017, starting 2017. Generates 1 gigaparsec cubed, so we can't use those simulations. What's happening? So SimBig actually cut down the size of the South Galactic Cap in order to be able to fit inside that 1 gigaparsec cube. All right, so this is the scaling problem. So the cost per actually generating 1 cubic gigaparsec, even though this is not hydro, right? Just n-body, is about 10 to the 3.5 CPU hours. And I will show you in a minute that if you just go about it in the straightforward way, you need at least roughly 10 to the 3.5 simulations to train your inferences. And so the cost for 1 gigaparsec of simulation volume, data volume, is about 10 to the 7 CPU hours. So it's not insignificant. And so I think the South Galactic Cap, or actually the reduced sized South Galactic Cap, is probably the last data set that we can really work with, fully nonlinear simulations. And this is gravity only, right? I mean, we're not talking about hydro simulations. So the challenge is a challenge of scaling. If you want to do this for DESI, you can't do it this way. You can't do it in a straightforward way of just simulating large cosmic volumes. So here it is, just illustrating this. So this is the main galactic sample in Sloan. That's high resolution, but much smaller than the sort of the scale hierarchy. But where we want to get to is things that are of order 100 cubic gigaparsecs. Okay, so then how do we deal with that? Well, our strategy within the Simons collaboration for learning the universe is to build high accuracy machine learning acceleration or emulation of full computational models. And then use them to reduce cost per gigaparsec cube by a factor of, let's say, 1,000. And the goal is to do this without sacrificing accuracy. So that's what we've been working on for the last couple of years. And so here's an example of a fast generative model that learns from n-body simulations. Again, I'm currently talking just about fully nonlinear n-body simulations and making those work in larger volumes for now. And so CHARM is an autoregressive generative model that takes an approximate simulation, so in this case run with fast PM, and then taking part of this as context, generates halos with various properties, masses, concentrations, that's a number of halos, and their properties in the center of a 100 megaparsec environment, 100 megaparsec cube environment. So Shivam is going to talk about this in more detail. And the thing is that this trains. The other good thing about this is this trains with a small number of simulations, at least for a given cosmology. When you vary the cosmology, then we have to run multiple simulations across cosmological parameters. So how does it perform? Well, it's about 1,000 times faster than running the full simulation, and so this allows you to do, when you have access to computing, it means you can actually generate thousands of these across cosmological parameter space, and then use that to compare to data. I'll just flash this to show that this works well in terms of reproducing various summary statistics, the power spectrum, bispectrum, wavelet scattering statistics. So if you're wondering what it is that I'm showing, actually showing the actual measured in full simulations, the quantities measured in full simulations in solids, and then the lines are on the same initial conditions run by Quixote. And you can then use this to do inference. So using, in this particular case, just getting cosmological parameters out of mock catalogs. So that technique now allows us to generate mock catalogs at scale. So I showed you the North Galactic Cup before. And actually comparing it to, this is the observation and plotted the same way. Here's for a particular set of cosmological parameters. And here it is for another set of cosmological parameters. So at a very rudimentary level, we are really comparing data and simulation directly. And so at this point, we will still be summarizing this in terms of intermediate summary statistics, but this is, it sort of starts showing where we're headed with this. And, I think by eye, you can see, for example, that these cosmological parameters don't work. They don't match. If you look at this, these seem to be matching better. Okay. Okay, so let's talk about model fidelity a little bit. So within this framework of accelerated forward modeling, the plan now is to use a sequence of parameterized model of galaxy mocks that are increasingly more accurate using semi-analytic models, hydrodynamical simulations, simulations with parameterized subgrid models. One of the things that we can do now, because we have these techniques, is to work with very large parameter spaces, tens of parameters. So we can run these simulations across large numbers of parameters for these SAMs and so forth, and then do inference using those simulations. And then at the same time, I showed you how to generate halos starting from n-body simulations, but in a minute I'll mention other techniques that are ready to be used for other outputs, other tracers, for example, galaxies and their photometry, which can then be used to do realistic survey selection, something that hasn't actually ever been done with spectroscopic surveys. They're generated by first taking image data and then selecting targets and then going after those targets. We could actually replay exactly that selection in our forward modeling to make sure that the selection function exactly corresponds to the way that the survey is selected. This is forward-looking. These are forward-looking statements, but that's the goal. Okay, so here's the next generation of these models that Shivam is currently playing with, which is using essentially, in words, the slide is just like you can ask ChatGPT to describe an image for you. We've trained a transformer model to look at a low-resolution n-body simulation of a given patch and then tell you what tracers you will find with what properties in the center of that patch. So in this particular case, this is generating halos with their masses, their positions, when shown a 3D environment. And so we're teaching a language model, essentially, to describe the halo distribution at the center of an environment coming from very fast simulations. So you can see we're exploiting the cosmic, one of the things that's special about cosmology is that you have this hierarchy of large scale being perturbative, small scale being nonlinear. So we're exploiting this hierarchy. We can generate the large scale environment using fast computational methods, physical methods, and then use fine scale nonlinear simulations to train these fast forward models. So this is very accurate and allows us to go a factor of 3 further in scale than CHARM. It's been tested in this first version down to about 1 K of 1 per megaparsec. And the technique here is the test is with halos, but the technique generalizes to any discrete tracer and their properties. So, you know, ultimately thinking about galaxies and their photometry, for example. All right, so this is the forward modeling part. What about the inference part? How many simulations do we actually need? I told you a number before, but where does that number come from? So let's do this with a very simple problem statement, and this is work by Anirban Bairaji, PhD student in Paris. The idea was to do the simplest thing possible, dark matter power spectrum. Let's get the cosmological information from the dark matter power spectrum using Quixote simulations. Okay, so here's the network architecture. It's just a deep neural network going from power spectra to parameters. The nice thing about the Quixote simulations is that we don't just have a Latin hypercube of different cosmological parameters. We also have this very nice, what I like to call the star. So a fiducial model with lots of simulations evaluating the statistics at that point, and then displaced parameter simulations in all the different parameter directions that allow us to compute the information content asymptotically at that point, the Fisher information. And so we know how much information there is in the power spectrum at the fiducial point. So if we train a neural network, how much of it does it get? Well, not very much. So the previous plot is actually now here. And this is the information coming out of the neural network. This uses the Latin hypercube of a couple of thousand simulations in Quixote. So even after extensive optimization of the network architecture, we don't actually get all the information out, even from the power spectrum. I'm not talking map-based, so this is the simplest kind of baseline thing that should work. And you can see, so if we actually throw away some simulations, you can see that we just haven't converged yet. As we increase the number of simulations, the contours keep shrinking. But we don't reach the Cramer-Rao information bound that we have available here. And so this gives you the idea for how to predict how many simulations you might need. Here are two different fits, a simple linear fit or a power law fit to these information points. And they suggest that you would need to get about 4,000 simulations to be in the asymptotic regime, okay, where you're approaching the information bound, whereas we only have 2,000 at the moment. And it turns out when you actually do that, it works. So if you go to, so the information bound is here, 2,000 simulation is the blue contour, and the green or red contour basically the same. Approximate that. So with about 4,000 simulations, you reach this asymptotic regime. So here's a way you can use to predict how many simulations you need. That's useful, but it's quite a lot. So how do we deal with that? Can we avoid running thousands of simulations at high resolution? Again, I think the answer here is to exploit the cosmological scale hierarchy. So you start with a large volume, but it turns out, all the nonlinear information is just on small scales. Why would you apply the analysis to the full box if you know that the power spectrum captures everything in the perturbative regime? So then just let's use the power of machine learning where we need it on small scales. So by just splitting this up into small patches and then training a neural summary based on now we're talking really at the map level, at the field level. We can combine it with endpoint information on larger scales to get a combined information vector that we can now train with a much smaller number of simulations, because we have a ton of training data for the neural network, and we don't need to train the power spectrum. We can use that in the traditional way. So just combining those together, you see that we get a field-based level of information which actually is competitive with the wavelets. This is not at full resolution. This is 8 megaparsec resolution, so I think wavelets are about the same on those scales. It's slightly faster and a little bit better in our tests, but comparable. And this is just taking the power spectrum and the patch summaries. If you combine it with the bispectrum, you squeeze out a little bit more, but you can see that you're really approximating the information content of the field. Lucas is going to talk about yet another idea which also combines traditional summaries with machine learning summaries to reduce the number of simulations needed. I'll skip this because for lack of time, but the goal is to use more than one data set, not just galaxy surveys, but other probes. Here are some examples for forward models that do that and there are some publicly available data sets that are very useful for this. Adrian is involved in this Half Dome work. Going beyond parameters, I mentioned initial condition reconstructions. So this is work from last year, showing that beyond parameters we can actually train conditional diffusion models to generate initial conditions that lead to, starting from a nonlinear output, we can train these initial conditions. So I think we can really get to an end-to-end understanding of how the structure assembles that we see in the sky. Again, I think this will be there will be many more ways to test the fidelity of the models with that approach. I think am I running out of time?
Yeah, you're a little late.
Okay, so I think I may only just say that give me two different simulation pipelines with two different models, two different halo finders, two different ways of modeling the galaxies, two different hydro simulations, two different SAMs. And I can just use Bayesian model comparison to tell you what the relative probability of those different models are. And it turns out the traditional way to do this is very difficult. With Nile, we looked at how to do this in a fully simulation-based way, and it turns out it's much faster than the current best-of-class traditional techniques, and actually more accurate for the tests that we've done. And it's near instantaneous once it's trained. So here are the conclusions. Look forward to your questions. Thank you.
Thanks, Ben. So questions? Yes.
So Ben, when you, for instance, were showing that for the power spectrum, you have the Kramer-Rao bound, so you more or less know. But in general, when you don't know the feature or it's maybe hard because you are doing a field level, how can you know the number of simulations?
Yeah, I think this works whenever you have a summary available, and then you have to, it's the combination of having the ability to do finite differencing and having simulations at a fiducial point that allow you to do this. Yeah. So, I mean, we've circled around this problem with this patch net. You've seen we've tried, combining all kinds of summaries together, wavelets with power spectra, these neural networks. And it turns out all of these approaches seem to, in the end, give you a similar result. So I think there's some, again, it's not conclusive. You can't a priori say how much information is there in the full distribution. But given that we approach this from multiple directions, I think the constraint I showed you is probably, for that resolution and this box size, is probably the actual information content. But there's evidence, but not a proof. Right?
So I guess my question kind of goes to the idea that, if you have really expressive subgrid physics models, with a large parameter space of subgrid physics models, is there a hope of using these types of techniques without having to run a massive grid of simulations? Like I was looking at like the Gizmo parameter input files, and it's of order like 40 subgrid physics model, subgrid parameters. And so if you're really going to be in a regime where you really need to do a big grid of these with sufficient volume to capture massive halos, if you're interested in doing cross-correlate, including both like galaxies and gas physics, how can one try to approach that type of scaling issue?
Yeah, I think I think it's already happening at some level. So Shai's been running simulations with 28 parameters, not many thousands, but a couple of thousand, I guess, at this point. And so so far so good. It seems that these techniques seem to still hold even when you have tens of parameters. And these are relatively small scale simulations, but they do cover a large range of parameters. And so the number of samples really are to sample the parameter space. I could imagine that one thing that we're trying to imagine also in the context of the simulation is to combine levels of simulations of different fidelity at different levels. So I mean, one thread of work that's ongoing is to improve subgrid modeling and run small-scale simulations, again, in a bunch of different environments, and then replay or emulate small-scale physics in as subgrid models in coarser-scale, larger simulations. So I think there have to be some kind of hierarchy of a nested simulation hierarchy if you really want to get all the way from black hole accretion to cosmological scales.
One last question. No? Yes.
Oh, thank you very much. My question is more conceptual. Like, I would be curious, what do you foresee for the future? Because now it's very difficult to have like a super large and good enough simulation suite for, let's say, stage 4 survey, given like a specific group runs something, then the other group runs something else because they are interested in some other probe or something like that. Do you think that that's the future, that people run their own, that very dedicated suite of simulations, or there should be something like a really field-wide effort to have like maybe some shared proposals, some unified simulations?
I think you're giving your own answer. I think we're here at a CAMELS workshop, and I think one of the valuable things that the leaders of the CAMELS project I think realized when they started this is that we need a community effort. And I think one of the really valuable outputs of CAMELS, aside from all the beautiful science, has been the creation of a community of simulators that are talking to each other and that are comparing these codes and that are running multiple suites of simulations. And so I think that's the way forward, given the expense and how complicated this problem is. I think that's the way forward, even for these large-scale simulations. But hopefully we can put together techniques that prevent. I mean, we simply cannot run a full-resolution hydro on Euclid scale. I mean, even running n-body on Euclid scale is extremely challenging, and I don't think has actually been done. Right? There's been 1/8 of the Euclid volume that's actually run in a single simulation, the Euclid flagship. So we're working at the forefront of what's possible, but I'm optimistic based on these, exploiting the scale hierarchies that we have available, and these emulator and acceleration techniques.
Okay, so thanks a lot, Ben.
Thank you.
And now we have Makinen, who will talk about galaxy property inference, I guess. So you have 15 minutes.
Can you hear me in the back? Give it 2 seconds. Right, so hi everyone, my name's Lucas. I'm based in London at Imperial. I am not going to be talking about hybrid statistics as Ben suggested.
Okay, sorry.
Something.
But
something
you could have.
Sure. I'm actually talking about some work that's been done primarily with Raj Pandya through the LTU connections program, looking at feedback modeling for galaxies. So this will be a story in 3 parts with a bit of a prelude. Again, we're in this sort of Bayesian paradigm where we have now replaced typical likelihoods or traditional likelihoods with simulators. We've got a lot of available simulators now to give us output galaxies, whether that's in a CAMELS box or exploiting dynamical system modeling or semi-analytic models to give you galaxy features. And of course, what we're interested in is sort of the inverse problem. So given the data we see, what model best describes the galaxies that we see in nature, whether that be at the level of parameter inference or indeed model comparison, now that we have a large buffet of available forward models for these galaxies. And Matt will talk after me about how we can go about modeling what is ostensibly a density, a likelihood function in probability space, whole different loads of parameterizations. And as Ben said, this was not possible 5 or 6, 7 years ago. So it's really remarkable what we're able to do. But I would argue, though, and this is part of the prelude, that if you like, let's say we have a perfect generative model of the universe that gives us a clone of the universe in all of its statistical features every single time, but we're not allowed to look inside of it. Have we really gained any insight about how galaxies behave and form? And we can simulate them. We can already do this. You can simulate galaxy images, but we'd love to know some of the inner workings. So that's kind of what we're looking at here. We're using semi-analytic models to figure out. So part one of this talk is Sapphire. This is sort of the galaxy formation model that Viraj and his collaborators have pioneered. And it builds off of decades of modeling, of galaxy feature modeling. And you guys in New York have probably seen this diagram around. It's a lovely cartoon of how you can model galaxies as a several-stage system. In this case, it's a two-tier system where the galaxy is interacting with the circumgalactic medium surrounding the immediate central galaxy, as well as the interstellar medium. And there's a load of feedback processes that are modeled using nonlinear ordinary differential equations. And those those take into account a lot of physical parameters that we care about, a lot of nuisance parameters that we don't, and also start to zoom in to the things that we do indeed care about in galaxy modeling. So again, these are all I want you to take away from this slide here is that we have some complicated descriptions, but not nearly as complicated as they could be. So we have labels and physical quantities associated with all of the terms in these coupled equations. And Raj, the big things that he's pioneered is adding in energy feedback modeling into these galaxy forward models to give us a more descriptive set of forward simulations. Cool. So let's zoom in on the feedback. Let's zoom in on the stuff that we care about. So if you're a CAMELS person, we consolidate what we call supernova or feedback parameters into a couple of scalar parameters that we vary across loads of different simulation suites. And we have an analog here in this Sapphire formalism, which is sort of the ratio of the stuff being made in the galaxy, the star formation rate, and the stuff being blown out via supernova feedback processes. And this ratio we call an eta, and we have an analog in energy space as well, which again is this ratio of stuff going out versus the stuff being made inside. So this is sort of what if we want to relate this to CAMELS, we can do. Viraj has done a lot of work applying this to simulation models. But again, this is a way we can consolidate understanding of astrophysics, especially if we want to take a step further to cosmology. There will likely be degeneracies with cosmological parameters. And indeed, these are a handful of numbers that we'd like to understand from data. So we can parameterize these fractions as power laws. Again, this comes from looking at data, looking at the outputs of simulations, again, over decades of work. And a power law model is a simplistic way to capture how these fractions behave according to the halo masses that these galaxies are sitting in, as well as the environments that they're evolving in. So these 4 parameters, the slopes and scaling laws of the power laws, are going to become the parameters of interest here. So I'm using conventional notation. So this theta is what we're going to what we care about. Okay, so that's part 1. Doing okay on time. Part 2 is fishnets. So this is the statistics bit of it in the simulation-based inference regime. So I'm not going to be talking about how to get densities, but I am going to be talking about how to consolidate galaxies from catalogs down to something usable for simulation-based inference. Okay, so I wasn't given a blackboard, but I like to draw these out. So what do we have? We've got a collection of galaxies. You can put this on a grid and connect them up via distance. You have a graph, but here we just have a set or collection of galaxies that are not connected and are sort of a grab bag in a bag of marbles. And each galaxy has some features, right, that we care about. You might have some virial mass, some stellar mass, some star formation rate, some feature that you can measure, whether it be a spectrum or downstream of an actual measurement. And what we like to do is we just like to write down what it is we want to know. We want to know the likelihood, given given a set of parameters of what this data will look like. And again, I put this data in brackets because it's a set of galaxies in this population that we care about. So if you just let me do a little bit of maths, again, I'm going to sort of breeze through this. I'm free to take the log of this likelihood, which I've done. I'm also free to take a derivative with respect to parameters through it. And indeed, because this is a collection, a set of galaxies that I'm considering independent, so I haven't linked them up, I can actually just sum up these log likelihoods to give you the global log likelihood. And it turns out that this derivative, again, I can just move that on the inside of the sum there. Turns out that this is called the score in statistics. But it's just a vector of numbers that changes according to the parameters as a function of the data and the parameters of interest. If you let me take another derivative, you end up with a matrix. And this is called the Fisher matrix. If, again, this is a distribution that proper distribution you're looking at. And again, these Fishers are also additive. So you can split it up. Each object in this catalog has some vector and some weighting matrix associated with it. Cool. So that's a curious feature. But then, if you're doing linear regression, and you know the form of these vectors and matrices, if you sum up all the weighting vectors, invert that sum, and then sum up all the embedding vectors and dot them together, you actually end up with a maximum likelihood estimate for the global parameters for that collection of things. And this is an exact solution in linear regression, but it's also just a useful form for a neural embedding that we'll get to in a second. And if you notice, if you have more objects, obviously you're going to have the sum of the weight matrices and the inversion of those weight matrices will give you a tighter set of error bars on the quantity of interest. So this all sort of makes sense mathematically. So in practice, we don't know the log of the likelihood or the Fisher. So we'll just pass this to a neural network. We're just going to learn the shapes of these two quantities. So some embedding vector and then some positive semi-different matrix to weight it. And then you can learn the form of these features by minimizing some sort of loss function. In this case, I'd like to keep the Fisher and the output theta hat statistic, but other loss functions are possible. I'll get to that slide if you guys have questions as to why I didn't use a deep set. But for those astute observers in the audience, that is another choice for this geometry of problem. But there's a very specific reason we don't use that. OK, so we can plug this in. And these error bars come from those weight matrices. We can test this within Sapphire. And we can see that, and we can do some sort of feature engineering. And loads of folks here have done this with CAMELS. Like if you withhold a certain bit of the data from the network, you're not able to recover certain parameters of interest. And in this case, it's very difficult to learn the mass feedback parameters without some additional features beyond just some stellar and virial mass estimates. But if you include some proxies or some measurements of the gas or the environment features, you're able to capture all of the parameters with much higher fidelity. So again, we can play this like sort of feature importance within the simulations, test it, things look really nice. And these error bars again come from this weight matrix that we're learning under this loss function. OK, I've budgeted my time perfectly. So now we're going to part 3. So again, we've looked at things within simulations. Everything looks really nice on the blackboard, and of course, everything looks great on paper. Most things look great in simulations. But now we're going to step to real data, because why not? The simulations look like the data. I'll show you why, and nothing's stopping us from doing the actual inference. So the manga catalog is, again, it's a consolidation of what was originally images and spectra of observed nearby galaxies that can then be consolidated into these summary statistics like adjusted stellar mass, star formation rate, as well as metallicity, gas and stellar metallicity measurements. Again, these just come from spectral features. So you take a look at, a cut of this manga data set. Look at so these are the data features, not posteriors. You can take a look at how they're distributed, and you can make some cuts so that they align with the simulation of the scales that we're able to capture in Sapphire. So we're just sort of cutting the data set, but what's really important is the forward simulations and the data are undergoing the same sorts of cuts. So you can see, again, this is just taking a simulation at random with we're not paying attention to the parameters that's generated here, but they do sort of line in the same plane. So what I'd like to do, though, is reevaluate this sort of statistical model that we talked about to take into account the fact that we're looking at real data. So again, things get a little bit more complicated when we go beyond simulations. So again, we have our model and nuisance parameters that go into Sapphire, which has a lot of differential equations going on. What we're going to introduce is some intrinsic scatter parameter that we're for each data feature. We're looking at a three-dimensional data vector for each galaxy, but there's going to be some level of uncertainty that we don't know. This could be due to lack of descriptivity in Sapphire. It could be due to some unforeseen systematics in the data, but this will represent some sort of distance between simulation and reality in data space. So we can take a latent version of the data and then pass it down to some actual sampled survey noise, which again is a different process to this intrinsic scatter. This is actually sampled from the catalog. We can add that at random to forward simulate these galaxies. We can apply some sort of survey cut, which is what we're doing, on these noisy features, pass that through to some sort of neural embedding model, come up with our feature vectors, aggregate everything together, and consolidate into some summary vector for each galaxy population simulated. And then for the real data, we'd pass that exactly through the same pipeline through to fishnets. Cool. So again, we can do this within simulations. Everything looks great. These scatter parameters that we've added, again, that describe the distance per object to the output of the model, we can actually infer. And again, they might be nuisance parameters later down the road, but because we've introduced them, we'd like to see if we can constrain them, and indeed we can. So you've got feedback model parameters, you've got some data scatter parameters. But then we can do this on real data. I'll maybe let this plot sit in the last minute or so that I have, in that we can actually obtain joint constraints on some statistical features of the model, as well as some physical feedback parameters of interest by comparing this to an actual catalog of SDSS galaxies. So we're taking a step. We were taking what was otherwise a really descriptive forward simulation, applying it to data, and now we have labels and features that we can actually work with and interpret from these posteriors. And then you can do all kinds of things, taking draws from these posteriors in feedback parameter space, and come up with predictive checks in data space to see how do your simulations line up with the actual data. And you can look at some data features that weren't put in, and you can see that for instance, in the data feature space that we've included in the model, we're able to capture rather well. Everything lines up nicely. But then for some of the features that we don't include in the data, we realize, in the inputs of the model, we realize that we might need to broaden the descriptivity of the Sapphire model. So that's my time. Thanks for your attention, and I'm happy to answer any specific questions.
Questions? Yes.
If I understand you correctly, that when you do this, putting the real galaxy information inside, you are limited to whatever the observation properties of those galaxies, right?
So, yeah.
Yeah, it's more or less related to the last plot you're showing that if there's some property which isn't presented, and which, to me, that the gas property, right, is more important for the feedback. So how do you deal with that? And somehow that you are missing the most important part, how you can make this constraint more tightly to the parameters, right?
Right. So the problem that we're confronted with is that we don't actually have a proxy for the gas temperature at the moment. So we're working with what we've got. So this three-part story, the middle part is sort of a message to observers to look for proxies for these features, right? That would tighten the constraints. That's what these predictive plots show, right? And then here, so the way we're kind of fuzzing out the data, right? And to again, we're not actually working with the folks that collected these catalogs, as we're adding in these intrinsic scatter parameters that we can infer, that tells you how far off per object your simulated data is from your real data, which is separate from the actual survey systematics, which is here is epsilon.
Okay. Not fully, but
okay.
Yeah, maybe we can talk about a little bit later.
Sure.
Yeah,
Yeah,
in detail. Okay, good. Thanks. Very nice talk.
Thanks.
You're in a simulations workshop when people treat surf formation rate as data or observations. But that's not the question. The question that I have is, have you compared, so this is in a way kind of an accelerated way of doing hierarchical population modeling.
Yeah.
Have you compared it to if you were to do the full Bayesian hierarchical model?
Yeah, so that is work in progress. That's in the sort of supplementary material. So this is not a BHM, but this is a, all of these simulations are differentiable. So Viraj is hard at work looking at, this is just an atom gradient descent explorer in parameter space, which is a precursor to the hierarchical model that will eventually run. What's difficult to do is come up with, I'm sorry, I've lost now signal. What is difficult to do is come up with, you have to assume some sort of explicit likelihood form for a hierarchical model. So that will be an ultimate discrepancy between simulation-based inference and the sort of this ground, if you want to call it a ground truth model. But that is, but you can choose from an array of explicit likelihood. So basically, what metric do you compare your target data with your sample data with at the last layer, the BHM? That'll be a choice, but that is work in progress. Yes.
Using rather than a actual likelihood, using some KL divergence of the two distributions or something like that, right?
Yeah. So at the level of the simulations, or at the level of the posteriors, you mean?
Comparing the two, the target distribution with your simulation distribution.
Yeah. So again, the metric itself can be changed. Sure.
About using manga, datamess, etc. And as we know, all those things are inferred in a certain way from this manga's IFU spectrum. So my question is, does the choice of different manga catalog affect the performance of your model?
So does a subsample?
Yeah.
So actually, so I don't have that plot on here, but the choice we made was the output. So the output of Sapphire gives you, and applying the same selection cuts on average gives you about 400 to 500 galaxies. So we use that fixed number of objects to compare to manga. So we subsample for 450 objects from manga every single time we run the inference. And what is quite cool, I should have put that in the supplementary slides, is that no, the posteriors do not change very much at all. So it is sort of robust to that. Again, you're grabbing marbles out of a bag. Grabbing a different set of 450 marbles does not change the inference in this case, which means that these statistics are robust. And I'd like to show you the plot. I'll show the plot afterward, if you like. Cool.
I'll go for the last question.
So last time I talked with Viraj, I mean, you didn't model satellites, or this has changed now?
Yeah, in this inference, we're not.
But then when you do a comparison with manga, I mean, you remove the satellites somehow, or?
So no, that would be a limitation or a missing bell or whistle from the model. So what you'd expect to see, so for an arbitrary feature that we might have mismodeled or forgotten to put in, if it affects the data features that we care about, it will make these scatter parameters smaller, right? So if we forget to throw something in, these will move a bit. The centers of these distributions will move a bit larger. So this is actually the log of the scatter. If we include more bells and whistles in the model, that means that the outputs of Sapphire become a lot more descriptive of the actual noisy data. So these parameters will tend to 0 or get pushed smaller. So that is a sort of an indirect way of doing model comparison in feature data space. As you can see, where do these inferred intrinsic scatter parameters go? because, again, we're free to vary them, we're free to infer them. So it's a sort of, again, this borrows ideas from, as Chang had said, population modeling from like supernovae and such. So we'd like to see that. Maybe it won't happen, but there are loads of bells, like I said, bells and whistles in Sapphire coming out, and we're free to do model comparison and feature importance studies downstream.
Thanks, Lucas.
Thanks, guys. Cheers.
So now we have Matt Ho, who I think will present the LTU pipeline.
No.
No. Wrong guess.
So, well, okay, simulation pipeline, not inference pipeline. So hi, everybody. My name is Matt Ho. I'm a postdoc at Columbia. I was previously a postdoc at the IAP, and I just moved to New York recently. So today, I'm going to be talking about real data, or our best attempt to get to real data using simulations. So there's been a lot of talk at this meeting, and also just in the field in general, is how do we actually touch real data with all these amazing simulations that we're making. And so what I want to talk to you about today is the learning the universe philosophy behind getting these high-resolution simulations of hydrodynamics and subgrid physics models to actually get to real data, to do inference and produce either constraints on astrophysics or cosmology in real life. So I've included a smattering of people on this slide who is a subset of the broader ragtag team that forms Learning the Universe. This is mostly the people who've helped with the slides, the work that I'm presenting today, but is far from the entire story. But what we are trying to do in Learning the Universe broadly is to say we have extremely high-resolution simulations that go all the way down to black hole AGN physics, ISM modeling. We have integration with the CAMELS people who are building subgrid physics models to bring those high-resolution simulations to cosmological volumes. And then we have a whole bunch of machine learning people who are trying to say, how can we get these cosmological hydrodynamical simulations into the large volumes which would be needed to compare to real data, right? And I live here. So my job for the past 2 years has been to build an implicit simulation-based inference pipeline to say when I am given data, I can accurately and precisely constrain the parameters that govern the physical models I'm interested in measuring. But what I realized is that simulation-based inference is easy to some extent, right? Training a neural network model, I can write a tutorial to do that and implement it in 30 minutes. However, what's really difficult is thinking about all the processes that you need to consider and all the assumptions that go into your model in order to really get to real data. I also want to mention I'm telling a very similar story to Ben, so please do not accuse me of plagiarism, especially if you see a slide that looks very similar, like this one. So, real data. Okay, let's talk about galaxy clustering sigma. We picked out this particular observational data set, the SDSS CMAS catalog, which is a catalog of galaxy spectroscopy that ranges from about redshift 0.4 to redshift 0.7. And it encompasses two catalogs. The Northern Galactic Cap, which is larger and shown here, which is about 3 gigaparsecs in scale, and the Southern Galactic Cap, which is smaller and about 2 gigaparsecs in scale. And as Ben did, for reference, this is the size of the Quixote simulations, which is about 1 gigaparsec. And to my understanding, it's the most frequently used data set for cosmological machine learning, because you have lots of simulations at a lot of different cosmologies, and probes almost basically at the right scale that you would need to touch the types of galaxies that would exist in the CMAS set. And so one might think, OK, how can I take the Quixote simulations and use them to perform real cosmological inference? Well, what you would do is you take your n-body simulations, your dark matter-only simulations. You initialize a universe with some random initial conditions. You evolve those initial conditions to the redshift of your sample, in this case around redshift 0.5. Then you find the halos in that simulation, either with a halo finder or some halo biasing model. Then you put galaxies in those halos with something like an HOD model, which is kind of what is necessary for this types of scale. OK, now you have galaxies in a box, so you want galaxies on a light cone. So you compute the redshift space distortions and the positions on the sky. And then you apply the masking effects that you would observe with the real data here. So you want to cut out all the regions where we might not have actually observed galaxies on the sky. And then you compare your real data and your simulations in some summary statistic space. So here I've shown the power spectrum measured from both the real data in black and my simulations in all the colors. And then you wave your hands and do machine learning, and you train on these things for which you have labeled data, and you try to predict on this thing, right? So this was the approach of SymBig, which was led by Cheng-Hoon Han, who's sitting in the corner over there. So what they did was they took the Quixote simulations, which are about 1 gigaparsec, and cut out a regime of the South Galactic Cap to do inference. So they applied all the HOD models, they did all the light cone extrapolation, yada, 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 and did machine learning. And this is my favorite plot from the Nature Astronomy paper that you guys put out, although there is a whole series of papers addressing a whole bunch of different statistics that you can measure from this catalog. And basically, you see that whether you use the power spectrum or the bispectrum or some field level inference with a CNN, you improve on the traditional power spectrum analysis done from analytic models by a factor of about 1.5 to 2.5. So you're shrinking the contours of omega matter and sigma 8 just by extracting more information from the field. OK? Now, I don't have time to go into all the results from SymBig, but you can definitely check out those papers if you want. But again, as Ben pointed out, the problem is that this approach, unfortunately, doesn't scale, right? So this is about the scale of the SymBig South Galactic Cap 1 gigaparsec volume that they use. But if you wanted to extend to the whole Southern Galactic Cap, or to the whole Northern Galactic Cap, or even to future surveys, which are extending over significantly larger volumes, you're going to run into a problem. If you wanted to run Quixote at the volumes necessary to simulate these large volumes, you would need on the order of hundreds of millions of CPU hours. And even more concerningly, you would need petabytes of data to store this on file, which is impractical under any regime. So as Ben pointed out, probably the last analysis we can do with these types of surveys, with this type of analysis, is the 1 gigaparsec analysis. OK, so we took a look at this, and we were like, OK, where can we make this faster and more efficient? And the parts I'm going to be focusing on are these parts here, which are the dark matter simulations and the halo biasing. OK, so the first thing we said is, what if we don't have to run full n-body? What if we can run an approximate n-body solver, like a FastPM method, right? So we ran FastPM methods at relatively high resolution, high enough to resolve friends of friends halos, but not high enough to resolve rockstar halos. And we compared what the summary statistics would look like when you used a FastPM simulator versus n-body simulator, or when you took a PM simulation and you use a friends of friends halo finder or a rockstar halo finder, or if you took these halos and then you applied a 5-parameter HOD or a 10-parameter HOD. And what we found is the results are all over the place, right? Like, yes, you could get reasonably good friends of friends halos if you ran PM simulations to high resolution that matched the n-body. But there was a significant difference if you cared about rockstar halos versus friends of friends halos, right? And so we felt that this was a problem. And even the storage capacity to store all the PM simulations was difficult on 3 gigaparsec. And so we wrote a paper to complain about it, OK? Then we were like, OK, let's take another tool off the shelf and say that, OK, I don't want to run halo finders, but instead I want to map the local density of dark matter to the counts of halos in a given voxel of my simulation. This is classically called local in-matter density biasing, in which the number of halos you observe in a given voxel is simply dependent on the dark matter density. But what we found is we couldn't find a single model which connected these two well to the scales that we were interested in measuring. And the proof of this is that we did something where we permuted the halo counts fields in a Quixote simulation for all the voxels which had a very similar local density. And what we found is that after we permuted this field, we moved things around, but to preserve the modeling which could exist here, the power spectrum was wildly biased. And so that didn't work. So there couldn't exist a purely local model to predict the halo distribution, to make our models faster. Instead, we needed to go larger. And we wrote a paper to complain about this. So this is not all about problems. This is about solutions. So Shivam produced this amazing model, which creates halo catalogs from low-resolution fast PM simulations. And Shivam is going to talk about this more extensively on Thursday. But the big takeaway is that you can input a low-resolution fast PM simulation and then output the positions and velocities and masses of halos distributed in a 1 gigaparsec volume. And the thing that I care about is that this not only works, but also it's 1,000 times faster than n-body simulations. So I can run 1,000 times as many simulations for this, which is really touching this regime where we need lots of training data that Ben mentioned. OK? OK, so all we have here is a halo biasing model trained on Quixote. So we would expect that it would perform well on Quixote. And in fact, it does. So this is an example of using this emulator to create the halo field instead of using an n-body simulation, and then training a machine learning model on this emulator and trying to predict using the full n-body test points. And of course, you see these red points, which are the halos that roughly trace the high-density regions of your simulation. You can measure Boove's favorite statistic, the wavelet statistics, and show that the Quixote points, which are shown as the squares, match the emulation statistics, which are shown as lines. So we're like right on the money in that regard. But really what we care about is the impact on observational inference. So here's an example of taking power spectrum, bispectrum, and wavelet statistics, mushing them all together into one big data vector, using HOD biasing models and redshift space distortions, just like you would in a real observational inference, and training on our emulated field and predicting on Quixote. Right? So in theory, if we observe the Quixote-like universe, then we would want to get good predictions when training on our emulator. And the result is that we are right on the money. Not only do we get tight constraints on omega matter and sigma 8, but also our constraints are well calibrated. So when I tell you that this is the 68th percentile confidence intervals, if the real universe is a Quixote universe, then then you have faith that 68% of the time the true value will fall in that regime. OK, so train on Quixote, test on Quixote, that should work. OK, what happens if we go to alternative models? So here's an example. Can I get both of these to spin? Nice. OK, so we were like, OK, we don't want to test only on 1 gigaparsec. Let's go to real volumes. So here's an example of taking the Abacus suite of simulations, which is another set of high-resolution n-body simulations, which were run at around 50 different cosmologies, and are about 2 gigaparsecs in volume, so significantly larger. And 2 gigaparsecs is enough to model the full southern galactic cap light cone. So what we did was we took this alternative simulations run by entirely different people with a different volume, a different gravity solver, a different halo finder, and a different mass definition. And we asked if we lived in an Abacus-like universe, would training on our emulated halo field associated with HOD galaxies produce unbiased inference? And again, through the same process, we applied galaxies, we measured the light cone effects, we measured summary statistics, and then we did inference. And again, we are unbiased. So here are the constraints of omega matter, omega baryon, H, NS, and sigma 8 when training on these emulated halo fields with galaxies and predicting on the Abacus simulations. And again, both Abacus simulations and our emulated halos exist in a real light cone. So they model all the redshift space distortions, all the systematic effects, all the galaxy biasing, et cetera, and not only do we get constraints which match true versus predicted, but also we are well covered in that our posterior error bars are close. And one more example before I finish is that we've also tested this on alternative galaxy biasing models, right? So what we've done is we've taken the closest thing we could find to a full, large volume, very accurately modeled light cone, which is the Millennium TNG large dark matter simulation, in which what they did was they have a 2 gigaparsec suite in which they calculated light cones on the fly and populated galaxies with semi-analytic models. So entirely different to our framework. And what we wanted to see was whether or not training on our halos plus HOD galaxies would be able to cover the cosmological constraints of Millennium TNG. And this is a slightly older plot, but basically what you see is the Millennium TNG point in orange following very closely to this 1-to-1 line against the backdrop of all of our test simulations. OK, so unfortunately, the unsatisfying part about this talk is that the observational constraints are not public yet. So we are currently in the blinding analysis of taking all that we've learned from this validation suite and comparing it against all these different simulations, and then applying it to real data. And that paper is expected in January of next year, so be on the lookout for that. Look for Learning the Universe CMAS inference. But nonetheless, the results that we found are I'm very happy with. This is, according to my understanding, the first application of field level emulators in an observational inference. We've shown that we are consistent across multiple simulations with multiple different configurations, with multiple different galaxy models. We are effectively marginalizing over the galaxy halo connection, even if we're not modeling it directly. And you might ask, Matt, who cares about halos? Why are we only talking about emulators? This is a galaxy conference. Well, in fact, we are actively developing new galaxy modeling to input into this simulation framework. And to hear more about that, you should listen to Lucia's talk today, this afternoon, or Chris's talk on Thursday. Thank you very much.
Questions?
Cheng, yeah.
Really exciting to see this all come together. I had 2 questions. The first was, I noticed that when you did the Abacus Summit, the Kmax value went from 0.32 to 0.2.
Did that change in the slides between the two?
No. I mean, like for Abacus Summit, it said 0.2, but then for the previous one, is this because you're doing a bigger box and the precision is now higher, and so the model misspecification kicks in earlier?
So the resolution works in, the resolution should be the same in all the simulations. The reason that it changed in that plot was simply because I just didn't have a presentation ready plot of the 0.32. We have been testing this. Basically, we'll have a validation paper which is supposed to investigate all these different Kmax choices and sees when we start to see bias between these external simulations and our simulations. And that's informing our observational inference. But from the internal results, 0.32 seems to be a reasonable metric for that.
Okay.
At least for the power spectrum monopole.
I see. So you're saying that, so even though the volume is now like a factor of 2 bigger in Abacus Summit, it's still fine at the same Kmax, roughly?
Yeah, roughly, yeah.
The other question I had is, you now are fitting the entire CMAS volume, and I was wondering, well, I guess one thing that concerned me was we imposed the redshift cuts in SimBig, partly because of the box and also because of potential variations in radial selection and HOD redshift dependence. And I was wondering if you put that into account in the forward model.
Yeah, so we've thought about that, the impact of redshift dependence on the HOD. We decided to go with a redshift independent HOD, but we haven't, at least with the semi-analytic model comparisons, we haven't really seen a need for it. However, I'm far from the world's expert on HOD models, so Cheng, actually, if you want to talk about this after, I'd love to hear more. Yeah.
There are also 2 questions from the audience. Should we? Okay.
Yeah, sure.
Cool. So the first one from Sultan Hassan. What we simulate is not the real universe, and observations will always be out of distribution. So once we have the fastest simulations, what is your plan to address the out of distribution generalization problem?
Oh, that's a really good question. Well, so, this is, as much as this is kind of a cop-out, this is how cosmology has been done with galaxy clustering for a while, which is like you have this HOD model and you hope that it fuzzes out all the things that you can model. But Sultan's right is that if we want to probe to higher and higher resolution, there may come a time where our simulations are, we could be at that time now where our simulations are not even close to the real observational vector. So we've been working on ways to adaptively filter out information that we don't want to be sensitive to in ways that are different than just applying a K-max scale cut and ignoring all the stuff that happens below that. That's still ongoing work, but you can imagine just thinking about using a machine learning model to weight the contributions of different galaxies or different scales or different environments based on how well we think we model them. And so that's very much ongoing work, but yeah.
Cool. And then the other one from Nathalie Soler Matobaro de Santi. Really nice talk. What was the number of observations you have used in the Abacus results for the TARP test? How does the number of samples really affect these tests? What about the other tests you have been developing as the other coverage test, rank, etc.?
Right. So we used all that were available in the Abacus emulator suite, which I think is like 50 something. Boreana, you know better than I do.
180? Or like 100 in the Latin hypercube?
Yeah, right. So that just off the top of my head, I might be forgetting that. But you're right. Like, so when we show this TARP test, I wonder if I can go back. So when we draw these contours here, which are supposed to identify when our model is good, the width of these contours is dependent on how many test data points you have. So the more test data points you have, the tighter these are going to be, and the more accurate you need to be in order to be well covered. So you're right. We only have so many Abacus simulations, and we can only nail this down so tight. How does this? OK. This is an example of a rank statistic test, except just in the multivariate posterior distribution instead of the univariate distribution. And from my understanding, this is one of the leading measurements of posterior coverage. Yeah, I can't think of other ones that we haven't thought about applying, but this is the one that I think everyone's been using.
We are already quite late, so
sorry.
I'm sorry. You'll keep the question for the break after the next talk.
Okay.
Thanks a lot, Matt.
Yep. Thanks.
Okay, so now we have Nicolas Cerardi, and I won't even try to guess this time. So this way I'm not wrong.
All right. Are you hearing me? Good. Okay, so good morning, everyone. What I'm going to show you today is the last project of my PhD that I recently completed at CCA Paris under the supervision of Margaret Pierre and François Lanius. So the topic is simulation-based inference for cosmology with galaxy clusters, basically. All right. So to give the motivation of this work, I would like to recall that galaxy clusters, they have the potential of being a very powerful cosmological probe because they are both sensitive to the growth of structures and to the geometry and expansion of the universe. So as such, there are like many different cosmological tests that can be done with galaxy clusters. And here in this talk, I will focus on the most popular one, that is cluster number count. So the basis of this number count analysis, you can get it from these simulations, and you see that so those clusters are marked by yellow circles. You see that for different cosmologies, the population of clusters is very different. It evolves differently through time. And so the underlying theoretical quantity behind that is actually the halo mass function, so number of halo as a function of total halo mass and a redshift. And what you see here is actually that the total halo mass is a very important quantity if you want to do cosmology with cluster number counts. So This is a problem because, of course, this total mass of clusters is not directly observable. So you need to estimate it from observations of a small fraction of the total mass. And this has been actually a major problem in cluster number count analysis so far. All right, so in practice, what we have access to is a sample of observed clusters, so a number of clusters as a function of some observable property, so here's the X-ray luminosity. And then the question is how to relate that to the Halo mass function, so how to translate the number counts between these two spaces. And for that, in cluster number counts analysis, traditionally we've been using the so-called scaling relations. So there are simple power laws between the observable properties and the total mass of clusters. And the existence of these scaling relations, in fact, is well explained by theory because it comes from the purely gravitational collapse of dark matter over densities. But however, what we observe is that the real observed scaling relations deviate from the theoretical expectations. So we have to resort to empirical fits with a very simplistic parametrization, so a power law plus an evolution parameter and an intrinsic scatter. And the reason why actually the scaling relations, I would say, the collapse is not purely gravitational is because of a variety of phenomena. So firstly, galaxy clusters are impacted by their environment. So the collapse is a triaxial. Clusters are connected to the cosmic web. And of course, they undergo merging events that strongly impact their observable properties, as you see here in X-ray. Also, of great importance for this talk is the impact of feedback processes, so AGN and stellar feedback, that actually hits the gas and also inject momentum into the intracluster medium. So this also greatly impacts the observed properties. So if we go back to our simple empirical scaling relation, parametrization, these few parameters here, they encapsulate at the population level all the different effects of these various processes. So the first problem we have with that is actually that this parametrization is degenerate with cosmology. And then, secondly, these parameters, they do not give us a direct link to the separate physical processes happening in clusters. So one thing that we hope for is actually to perform the cosmological analysis of cluster samples without using these empirical scaling relations. And for that, in my PhD, I've been using simulation-based inference and modeling tools to develop a new method for this kind of analysis. All right. So going back to this sketch, firstly, I should precise that instead of using the luminosity function here, I represent the galaxy cluster population in a three-dimensional X-ray observable diagrams, so meaning representing the cluster population as a function of redshift. Here it is projected on X-ray flux and X-ray color. And this three-dimensional representation here, in fact, has as much information as the mass redshift plane here. So we want to find a new way to forward model the galaxy cluster population into this space without using these scaling relations. And so naturally, we can think of simulations, hydrodynamical simulations, because they directly incorporate the different physical processes that impact galaxy cluster observable properties. Of course, it's too expensive to be used over inference. So what we would like to do is to actually accelerate, emulate these simulations with a machine learning approach. So meaning replacing the explicit Halo mass function and explicit scaling relations we traditionally use by an implicit simulation-based framework. All right. So at the heart of this method, there is a baryon pasting model. So not the first one you see at this workshop. But so the first question I will try to answer is, can we learn a fast and accurate baryon pasting model? And secondly, what is the advantage of that during inference time? And this is the subject of a paper that will be likely submitted next week. So for the baryon pasting, I've been using and adapting the Lagrangian deep learning approach proposed by Dai and Seljak. So it's a fast emulation of the full three-dimensional field of some baryonic property. And here, because I want to emulate the X-ray emission of galaxy cluster, actually I'm interested into modeling the electron number density and the temperature. And so just to give a bit more details about how this model works, basically it adopts a lot of physical principles because you will move your dark matter particles along to some potential, and this potential is corrected into Fourier space by a one-dimensional Fourier filter, which is here a B-spline. And so you will have an updated field and pass this updated field into a nonlinear activation layer. And then all the red parameters here are the weights that you have to learn in order to recover the appropriate, the target baryonic property. So the main advantage of that is that it's a very light model. Most of the weights are here in the B-splines. And it's much lighter than deep generative models. So it's actually, you can train it on a reasonable amount of data. So that's the main interest. So that's good for one to reproduce one given simulation with a given set of simulation parameters. But for for this purpose, we want to go one step further by conditioning the baryon pasting model. Okay, so we want our baryon pasting model to be dependent on the cosmology, but most importantly, on the feedback. Okay, so in the meta-learning approach, what we do instead of learning directly the LDL baryon pasting parameters, we train a neural network that takes as input the simulation parameters and that outputs the LDL parameters. So, of course, I've been training this model using the CAMELS simulations in several steps. So, firstly, taking the CV 50 megaparsec cubes to train the base LDL model, and then training the conditioning on the LH boxes of 25 megaparsec. And then there is also a third step of conditioning to have a dependence on redshift by just duplicating and retraining the model at different redshifts. All right. So because here we are using, I was using the first version of CAMELS, we have like 2 cosmological parameters, but also 4 astrophysical parameters for the conditioning. All right. So we can quickly have a look at the emulated field. So here I'm showing like one baryonic property, the electron number density. You have the target from CAMELS here. You have the LDL reconstruction. It's not completely perfect, but it's much, much faster. And then here we can look at the end product of our modeling because this is the X-ray emission. So you have the input dark matter field. You have the true X-ray flux from CAMELS. And you have the LDL predicted reconstruction. So it looks to be in reasonable agreements, but what we want is really to assess the quality of our model on clusters. So we embed this baryon pasting model into a full simulation and detection pipeline. So running dark matter only simulation with the JAX PM code, then performing the condition LDL approach to have the to paste the baryons. And then we populate light cones, and we use the XMM Newton instrumental response to generate X-ray MOX. So here you have like several samples generated with different simulation parameters. And then afterwards, we can run a simple detection chain. So we assume that there are no point source in the field, and we just detect clusters. We measure their X-ray flux, their X-ray color, and we build these three-dimensional summary statistics that we usually have when we use the traditional modeling. So the strength of this approach is actually that the simulation side is all compiled on GPUs. It runs on the French Janzé supercomputer. And to have a few tenths of square degrees of the X-ray sky, you just need a few tenths of seconds. So it's really efficient. It actually enables the use of such a modeling for cluster number counts analysis. So now we can look at the results at the level of clusters. So here I'm showing you the relation between the X-ray flux and the total mass. in blue for the true CAMELS cluster, and in red for the LDL emulated clusters. All right, so you see that we recover very well the mean tendency of the cluster population, but what is also very important for us is that we also recover the intrinsic dispersion around the mean, okay? So it means that at the population level, we recover the same statistics that we will do with the traditional modeling. But in fact, what we do is a bit more interesting, because if we were just doing like empirical scaling relations, at the individual cluster level, we would have no correlation between the true and emulated X-ray flux. But here, because actually the LDL benefits from the three-dimensional information on each halo environment, we have now a very nice correlation here. So it's very interesting. And this test is actually done on the CV set of CAMELS, but unfortunately we don't have enough clusters in the LH set, LS boxes to conduct the same test. So here it's one of the limitations of our training data, but at least this is encouraging. So now we can look at the sensitivity of our model. So here I'm showing you the number of clusters detected in 50 square degrees X-ray surveys as a function of the simulation parameters. And you see that for the cosmology, we are very much sensitive to it, so it's reassuring. And then looking at the astrophysical parameters, we are strongly sensitive to the stellar feedback and weakly sensitive to the agent feedback. So this is quite a surprising result, because at the scale of galaxy clusters, we would expect just the opposite. And so some answers to that is firstly the fact that, in fact, the strong impact of stellar feedback here is because stellar feedback acts on the agent feedback, it regulates it. So here, in fact, is a physical, this is like the physical trend that we see. I mean, it has a physical explanation. Regarding the sensitivity to AGN feedback, in this first version of CAMELS, there are more agent feedback parameters that are here fixed, and some of them are known to impact the X-ray properties of halos. So it means that if we want to apply our method on real data, we need actually to condition our model on a larger set of parameters and using a more complete training simulation suite. But still, we can, as a test, look at the behavior of this model over inference and see whether it's interesting or not. And so here so we don't perform directly the posterior estimation on our three-dimensional summary statistics. We use a neural compression with a deep convolutional network. And then we perform the direct posterior estimation on the compressed statistics here. I'm a bit out of time, so I think I will skip that. But here, so because actually our neural compressor is acting as a regressor, we can look at the regression plot, and you see that we recover a lot of information on the cosmology. We also recover some information on the stellar feedback, and much less on the agent feedback. So this is well related and explained by what I showed earlier. All right, so now we can look at the cosmological posteriors. Here in blue, posterior estimated with our simulation-based pipeline, and in yellow here with a scaling relation-based modeling. And why is there such a strong difference? Is actually because of the degeneracies in the model. So here, for the explicit model using empirical scaling relations, you have 2 cosmological parameters and 6 nuisance scaling relation parameters. So this is cosmology and scaling relation. And you see that there are many degeneracies. And then, looking at the simulation-based, the full posterior for our simulation-based model, actually now we have much less degeneracies. And in addition, we now can have constraint on parameters that have a physical sense, okay, astrophysical parameters. All right, so I'm leaving here the main points of this talk. And just as a final word, just want to advertise that in my postdoc now at EPFL, I'm working on non-CDM simulations, again, to accelerate and emulate them with machine learning. So if you are interested into that, I would also be happy to chat about it over coffee break. Thank you.
I was curious whether CAMELS doesn't have a lot of clusters in the catalog. Is that what necessitates the Lagrangian deep learning, because it's a light network, so it's easier to train even though there's fewer data, or is that not an issue at all?
So in fact, we wish to have more clusters, so like to actually try to train this model on larger boxes. That's why we firstly train the base LDL on the largest boxes we could. But then it's sure that actually the conditioning that we have learned is learned on small groups. Okay, so this is also something that should be improved by training on larger boxes.
Yes, Chris.
Yeah, great work. I just had a question about the cluster profiles in the 50 megaparsec box. Do they look realistic in TNG and that sort of mass scale in terms of temperature profiles and in entropy profiles? And I wonder, yeah, the sort of second point would be, I wonder how much the lack of dependence of the AGM feedback is on the limited mass range of your clusters. Could you comment on that?
Okay. So, so first point, can you remind me the first question? It was, sorry.
Just about the entropy profiles, temperature profiles.
So actually studying the profiles, like temperature, density, entropy, is like a very good point. This is not done so far, so we want to do it next. But regarding illustrious TNG, looking at the, for example, the X-ray luminosity of clusters, it's fairly in agreement, in reasonable agreement with observed samples, maybe like with a smaller dispersion. So this also like could impact our results. And the second point was on. Sorry.
It's just about the AGM dependence, whether you expect that to extend to sort of 10 to the 15 M solar clusters, or.
Yeah. So here, like we have halos up to 10 to the 13, 10 to the 13.5. So I mean groups, which is where actually the AGM feedback should be impact on. So we should have some dependence here.
I think we'll go for a break now. Thanks, Nicolas.